All right, this is the second lecture of chapter 2. This lecture is going to really focus on naming chemical compounds. So there's just a little bit to add as far as theory goes and bigger concepts, but otherwise it's just getting into the nitty-gritty of naming. So without further ado, we finished our last lecture with a slide that talked about the kinds of bonding that we're going to explore, and primarily that's going to be ionic bonding and covalent bonding. So we start with ionic. So you've already seen this figure, or one very similar to it, which shows the transfer of an electron from a sodium atom to a chlorine atom to create a positive sodium ion and a negative chlorine ion. So the first thing to take note of is that we have a specific name for those kinds of ions. So if you have a positive ion, like our sodium here, that is called a cation. And our negative ion, chlorine, would be called an anion. So I remember this because a cation is positive, right? And an anion is a negative ion. Right, so anion, cation, really important to have that vocabulary down. So ionic bonding is going to have a couple trends to it that are really helpful to orient yourself in how to name these compounds. So the first thing that we just talked about is that an ionic bond is going to involve the transfer of electrons. They occur between a metal and a nonmetal. And as illustrated here, the metal is going to be the cation and the nonmetal is going to be an anion. Okay, so cation means that it becomes positive, meaning that it donated an electron in the formation of the ionic bond. Anion is negative, meaning that it accepted that electron. So if you remember our staircase here that separates our nonmetals from our metals, right? Nonmetals all being this part of our periodic table plus our hydrogen, and metals being everything else. There is a trend that explains this phenomena of nonmetals always forming our anion, and that is electronegativity. So electronegativity is going to increase across periods and increase as you go up a group, right? So I like to think of that as being an aggregate vector of going from francium to fluorine. So fluorine is going to be the most electronegative, which we just abbreviate as En, and our francium is the least electronegative. So what does electronegativity mean? Electronegativity is an element's like attraction to, which you can also think of as being like a draw, like for an electron. Okay, so let's just get that back up here for a second. So properties of ionic bonding: transfer of an electron. You have a metal plus a nonmetal. And then that trend that I just mentioned, you have a difference, usually a large one, in electronegativity. And that difference in electronegativity is going to explain why sodium gives up that electron and chlorine takes it, right? Sodium is here, chlorine is here, and our electronegativity trends go like this. So chlorine is much more electronegative than sodium. And so we have this like larger difference in electronegativity. So once there is this transfer of electrons, as is shown here in our sodium cation and chlorine anion, they're going to be held together. So this would be force by electrostatic force. Right? So what that's saying is that their opposite charges attract, right? Okay. So those are some principles of ionic bonding. And now we're going to look at the periodic table and how the periodic table kind of tells us what charge these ions are going to have. So group 1A, which is those alkali metals, are going to form a positive 1 cation. So the metal, again, is going to be your cation. Non-metal is your anion. So here we have a group 1A, positive 1 cations. 2A is going to form positive 2 cations, and this has to do with their electronegativity and also, and this shouldn't be surprising, but because of their electron structure. So the way their electrons are configured in the atom. That's ultimately what drives all bonding, as we talked about in lecture 1. So we're going to leave the specifics of this to chapter 7 and 8. But for now, just remember these trends and keep in mind that they are true of the whole group. In this case, inclusive of hydrogen. And that has to do with, again, their electron configurations. And remember that groups tend to have groups do have the same, very similar chemical properties. So 1A forms a positive 1 cation, 2A positive 2 cations. Group 7A is going to form a negative 1 anion. Group 6A forms a negative 2. And then you can see some additional trends that are highlighted here. So group 5A, nitrogen and phosphorus, are always going to form a negative 3. This has carbon as forming a negative 4. Carbon really doesn't form an ion. Carbon always wants 4 bonds. And that's something that we'll, again, explore in future chapters. So I would kind of like ignore that right now. But these are the big trends that we're going to pay attention to while we first explore ionic naming. The trends listed here for our transition metals, remember that's this section of our periodic table, that's going to come into play on just a couple slides from now. But right now we're going to focus our attention on the representative elements, right? Remember those are those elements in 1A, 2A, and then 3 through 8A. Then we'll delve into the transition metals. So this kind of naming is called type 1 naming. Why? I don't know. They named it type 1 naming. So when you're naming a type 1 compound, the first thing to recognize is that all of these compounds are ionic. Right? So type 1 and type 2 naming are going to be about ionic compounds. So that makes sense when we look at the structure of the name. So you have the cation name plus the anion plus the ending IDE. And this is a really big consideration, which is that the anion and the cation charge are going to equal 0. That's what gives them their stability, right? They're held together by electrostatic forces. So first, let's explore these type 1 ionic compounds that are just with monatomic ions. Monatomic meaning a single atom. So here we have Al, which if you should have it in front of you every lecture you watch. If you identify Al on your periodic table, you'll see that it's in group 3A and that it is aluminum. Right, so we just name our cation, and then we need to find our anion, which would be O, which is oxygen. And so oxygen is a good one to use as an example because the IDE ending is a little less intuitive. So oxygen becomes oxide. if you notice, we have this cation charge and anion charge equals 0. So let's just look at what that means. And I have the table from the last slide, the periodic table with the charges on this slide for us to reference. So if you identify oxygen there, it says that that is a -2. And then aluminum, if you find it right here, is going to be a +3. So remember, our subscripts are going to modify the element that precedes them. So that means that we have 2 aluminums. So if each aluminum is a +3 cation, that means that they have this overall charge of a +6. For our oxygen, each oxygen has a -2. So the total number of anions, 3, gives us a charge of -6. So if you were to add those two values, they equal 0, which means that we have a stable and correct compound. Okay, so let's explore this next option. So we have bromine. Bromine is right here, so that's a -1, giving me an overall charge of -2 because I have 2 of them. And then calcium is right here, that's a +2. So it makes sense that they would be in this configuration. And that would be named calcium bromide. So in this class, anytime you're given a compound, you can assume that it is correctly written and balanced. But this is just a good kind of exercise for when we graduate to this next level. Excuse me. I'm allergic to my dog. It's fine. The things we do for love. Okay, so this is more type 1 naming, but now, excuse me, now we're going the opposite direction. So before we had the compound formula and we were naming it, now we're going from name to compound. So this is a little bit more difficult, but there's a nice kind of flow that I like to use that I encourage you to try out and see if it works for you. So we have sodium and bromide. So the first thing that I like to do is just identify the symbols for those elements. So sodium is Na, bromide is Br, sodium, bromide. And then above the written name, I like to just write what their charge is, right? So sodium is a +1, bromide is a -1. So sodium and bromide would just be NaBr. So I might just neaten that up and be like, okay, that's my compound. Okay, now we're going to look for strontium nitride. So strontium is this one, so that's Sr. Nitride is nitrogen. So strontium is a +2. Nitrogen is a -3. So I need these to equal to 0. So I need to look at 2 and 3 and determine what the least common factor, the lowest common factor is, and that would be 6. Right, so 2 times 3 is 6, giving me an overall charge of +6. Nitrogen, 3 times 2 is 6, so that would give me an overall charge of -6. You add those two values together, you get 0. So this is the combination that students usually find the most difficult, and one kind of shortcut that I like to highlight is notice that nitrogen's charge is -3, and that became the subscript of strontium. Strontium's charge was 2. That became the subscript of nitrogen. Right, so we don't have subscripts if it's 1, because we're chemists and we don't write anything unless we absolutely have to. Scientists are big fans of brevity. That's also true for any answer that you write on like an open question, like in your labs. Short, succinct, to the point, show me that you know the problem, so show me that you understand, in as few words as possible. I'm obviously not the most succinct in my language, at least when speaking, so I won't hold it against you if you weren't either. Okay, so that's type 1 with monatomics. You can also have type 1 with polyatomics. So typically in a chemistry course, the very first thing that you have to do is memorize polyatomics. But in this course at SMCC, we have the polyatomic ion list on your periodic table. So you don't have to memorize it. Eventually, after this chapter, you'll have many of them memorized just from consulting this table so many times. But if you look at the table, you can see that you have the name here. This is the formula for the ion, and then we have the charge written next to it. So remember, those charges again are always written with the number and then the charge. So name, formula, charge. Okay, so in naming a polyatomic type 1 ionic compound, you name the cation and then you just give it the polyatomic name. Okay, again, the cation charge and the anion charge have to equal 0. So this is Na, looking at your periodic table, which of course is in front of you, is sodium. And then I have CO3, and I'm going to identify that over here. Right here. So that is going to be sodium carbonate. Right, so we just want to make sure, like, does this make sense? Yes, sodium is positive, carbonate is a -2, so I have 2 of those for every one of those. Yes, that makes sense. Now, if you were just to look at this formula, your big clue that this is a polyatomic and not a monatomic ionic compound is the fact that you have 3 uppercase letters. So if you look at your periodic table, you either have an element like oxygen, which is just 1 capital letter, or an element like chlorine, which is a capital letter and a lowercase letter. So each capital letter essentially is representing a different a different atom, or in this case, a different ion. So this is 1, 2, 3. That lets me know that it's polyatomic. Poly meaning more than one, or many. Okay, so this is sodium carbonate. Here we have potassium acetate, so going the other way, right, where we're analyzing from the name to writing the formula. Here I have potassium. Potassium is positive. Acetate, right? So remember, from monatomic ions, the ending is IDE. ATE is not an IDE ending, so that's your indication going from name to compound that you need to consult your polyatomic list. So I want to find acetate, which is right here. It is a -1 charge, so that means I just need one of them, so that's KC2H3O2. Okay, then we have calcium chlorate, excuse me. So that has calcium as a +2 cation, chlorate, right, ATE ending. I know that that is a polyatomic. I find it right here. So chlorate is -1, which means I need 2 of them. So we have ClO3, and then we put parentheses around that polyatomic, and we indicate with a subscript that there's 2 of those. So polyatomic ions are covalently bonded to each other. They're really stable together. They will form an electrostatic attraction or ionic bond with another, with a charged particle in their solution, in this case, because chlorate is a negatively charged polyatomic or an anion. It's going to form a bond with a cation that's in solution or in their environment. So it's really important that we indicate that these are covalently bonded together, that this is a polyatomic ion, and that we have 2 of them. So those parentheses are super important. Okay, so that's type 1 naming. Now type 2 naming is basically just a extension of type 1, but type 2 naming is going to be dealing with these species in our transition metals. So if you look, like here we have lead, and it says Pb2+ or 4+. So transition metals are they're not representative, they're not as predictable, they have some really interesting characteristics. I'm not an inorganic chemist, so I don't, this is not my wheelhouse, but they are really interesting. and they can form multiple different cations. So that's like the big kind of chemical understanding of transition metals to get under your belt right now, is that transition metals can form cations of more than one charge, right? So if you look at 1A, everybody is a positive 1. 2A, everyone forms a positive 2. Here we have everybody in the halogens forming a negative 1. Group 6A forms a negative 2. So transition metals, they could form, like looking at iron, you could have iron 2 or iron 3. So we need to be able to indicate which form of iron is in the ionic compound that we're working with, and the way that we do that is with Roman numerals. So here's a nice kind of review of Roman numerals if you haven't used them for a while, because you're going to need to remember. So we write the cation name, and because the cation could have multiple different charges, we use a Roman numeral, which is going to indicate the charge of the ionic, let's just say of the ion. Specifically the charge of the cation, right? So cation charge. Then you have the anion plus your IDE ending. So here we have Mn, identify Mn on your periodic table. That is manganese. It's with oxygen, which is oxide, right? But I need to tell my audience which form of manganese that is. So what's important here when you're working with a transition metal and you're going from formula to naming is you just need to look at the anion, because the anion is going to be a representative anion, so it's always going to have the same charge. In this case, oxygen always has a charge of negative 2. So because manganese is paired with oxygen and there's only one manganese, that means that manganese has to be in the positive 2 form. I would recommend writing these possible charges on your periodic table, because it's really nice after doing this kind of analysis to say, okay, that checks out. Manganese does form a positive 2 cation. So to write this out, I would say manganese 2 oxide. Now the reason why this Roman numeral is so important is that if I had the name, but I didn't have that Roman numeral and I had to write what the formula is, that could be MnO as it is here, or if it were manganese 3, then that would be Mn2O3. Right? And these compounds are going to have very different masses, which is going to be very important when we get to chapter 3. So do not forget your Roman numeral, super important. So 10 is Sn. That is a positive 2. Nitrate is in group 5A, 3 minus, so it's Sn3 N2. Right? Again, we have a good illustration of why that 2 is so important. So don't forget those. There's a reason why it's included. You wouldn't know how to write the correct formula if you didn't include the Roman numeral. Again, Roman numeral tells you the charge of the cation. Anion is going to be the same. That's not the part that has variable charge. Okay, so that's type 1 and type 2 naming. Type 3 naming is looking at covalent compounds. So covalent compounds are different than ionic compounds. So in our ionic compounds, we always had situations where you have a metal and a non-metal. So you had something like, we had strontium nitrate, I think is one. Right, so looking at our electronegativity chart, knowing that we go from the least electronegative to the most electronegative, you can see that there's this pretty significant difference in electronegativity. With our covalent bonding, our example here is oxygen and hydrogen. And here it's important to recognize that hydrogen is actually, as far as electronegativity goes, like I said in the first lecture, it would be nestled basically right beside carbon. They're almost the same. So here we have our hydrogen and our oxygen. Those are much, much closer on the periodic table. They have much more similar electronegativity. Because of that, instead of the one element being able to attract an electron and keep it, right, to have that transfer of an electron, oxygen and hydrogen are going to share electrons. So the whole reason why bonding occurs is because the species involved in bonding, by species I mean the elements, the atoms involved in bonding, they are more stable once they form that compound than they are apart. And that has to do with their electron configuration. We're not going to get into that in this lecture. It's something that we'll focus a lot on in chapter 7 and 8. So just suffice it to say that electrons are the subatomic particle that's involved in bonding, and covalent bonds form because you have a more stable compound. Ionic bonds do as well, but all bonds form because you achieve greater stability. Covalent bonds, you don't have enough difference in electronegativity to strip the electron from a cation to an anion. Instead, it's going to be a sharing of electrons. So there's a couple trends, just like we saw in ionic bonding, that we want to explore. The first one is that these are going to be bonds between a nonmetal and a nonmetal. Right, so remember, hydrogen is over here, but it is a nonmetal. Here you have the sharing of electrons, unlike an ionic bond, which is a transfer. And they're sharing because they have similar electronegativity. Okay, so that's our introduction to covalent bonding, and what we're going to see is naming covalent compounds is actually a breeze. So what you need to know are these there we go. What you need to know are those prefixes. So you want to have these, I would recommend just like somewhere on your periodic table. You could write them on the back side with your other kind of tables that are provided for you or wherever you want. But what's important is recognizing that you have these prefixes which are associated with this number of atoms. So we have mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. So as you hopefully continue your chemistry education, because chemistry is the best. If you get into organic chemistry, you will become intimately familiar with these prefixes. But for now, we're really just kind of analyzing some simpler compounds. They're always going to be diatomic, meaning 2 atoms. And so we can just name these pretty simply. And the way this goes is you have your prefix, then your nonmetal number 1, prefix nonmetal number 2, and then IDE. So Si, we want to identify that on our periodic table. That is silicon. We have 2 of them. We see that that prefix for 2 is di. So this would be disilicon, right? We have 6, which is hexabromide. Okay, now we have N, and we have 1 of those. And what's important to recognize here is if we have like NO2, like we do here, the first element listed is, we only have 1 of them. We don't use the prefix mono. If it's the second element, then we do. So I'll demonstrate that in a second. So here we have nitrogen, right? And then we have 2 oxygens. Dioxide. If instead we had CO, right, carbon, right, we only have 1 of those, but we don't use mono for the first element, and that would be monoxide. This is a nice illustration of that. Going the opposite direction is a breeze with these, because you just say, okay, this is nitrogen, di means I have 2, this is oxygen, pent means I have 5. So great, right? Ionic compounds, you have to give a little bit more consideration. Covalent is pretty straightforward. Your recitation packet has examples of all 3 of these namings. And then there's a worksheet that I posted that also has a key on it that I really encourage you to work through. So one thing I will say, students sometimes get hung up with type 2 naming with the transition metals and what their charges can be. But what you need to focus on is what the anion is. So if you have 2 oxygens, no matter what the cation is, whatever transition metal it is, if you have 2 oxygens and you only needed 1 of that cation, that means that that cation has a positive 2 charge. So you can deduce the charge of your transition metal by examining the anion. So focus on the anion in type 2 naming. Okay, so here's a really nice flow chart from your textbook. I recommend that you refer to this while you're working through problems and worksheets. So the first question is it a binary compound? So binary means like 2 parts, right? So this could be any of the compounds that we've talked about up until now. So your answer is always going to be yes, so we could just forget that part. And then your next question is there a metal present? If there's no metal, then that means that it's a covalent compound, right? Covalent compounds are between nonmetals and nonmetals. That tells you that it's type 3 naming and you're ready to move forward with prefixes. Alternatively, if there is a metal presence, then you have further considerations. So one of those considerations is if it's a transition metal, or as this says, does it form more than 1 cation? If your answer is no, then it's type 1. If your answer is yes, it's type 2, and you need to use those Roman numerals. So this is a really helpful flow chart, especially as you first get practice with naming. So we have a few more types of naming that we're going to explore. The first one is naming acids. So we'll use a lot, we'll have a lot of reactions that involve acids. Acid-base chemistry is a huge part of biological systems. It's something that we'll dive a little deeper into when we get to chapter 4. So we're just going to do a brief introduction, and for whatever reason I decided that this was a good I don't know, clip art from the early 90s. Maybe it reminds me of when I first took chemistry. So you have an acid and you have a base. You've probably heard of acid-base chemistry before. And what we want to focus on here is that we're going to define an acid as a proton donor. Okay, so we haven't talked about what a proton donor would be, right? We've talked about protons and neutrons and electrons, but a proton donor is going to be a hydrogen ion. Right, so if we look at our periodic table, we'll see that hydrogen is in group 1A. It's a non-metal, but the reason why it's in group 1A is because its bonding trends are similar to those of alkali metals. It's going to form a positive 1 ion. So that would be represented as H+, which is a hydrogen ion, which is a proton. Why do we call it a proton? Well, if you look at the hydrogen atom, you have a nucleus, and then you have your electron, one single electron orbiting it. So normally we think of a nucleus as possessing both protons and neutrons, but remember that neutrons are there to stabilize the charge-charge repulsion of protons in the densely packed nucleus. If there's only one proton, as we see in hydrogen, right, its atomic number is 1, we don't need a neutron. And in fact, hydrogen doesn't have a neutron. So it's just this one single proton. So if we have an ion of hydrogen and it loses this electron, well then it's just a proton in the world, which is why we call it a proton. So acids is going to be a proton donor, and bases are going to be proton acceptors. So an example of an acid would be right here. So we have HCl, hydrochloric. Never mind, I didn't say that because we haven't named it yet. We have HCl, which is an acid. And when that goes into like an aqueous solution, it's going to end up as two ionic entities. So we have our cation, our proton, and then our anion, chlorine. So HCl would be an acid. If we have let's say we have barium hydroxide also in solution, right? That will actually dissociate into yep, sorry, that needs to be a 2. I wrote it and was like, there's something wrong here. Barium hydroxide, if that went into solution, it would look like this. This isn't the most important part. But what's important is that a hydroxide, if it's in an environment with a proton, you're going to have what's called a neutralization reaction, where you have your proton and your hydroxide forming water. So it's just a little, like, very brief intro to acid-base chemistry. All you need to really focus on as far as naming goes right now is that acids are going to always have hydrogens. So acid has a hydrogen. Right? Okay, so if you have an acid that doesn't have oxygen, so we have 2 conditions for acids, with oxygen and without. If it doesn't have oxygen, then we write it as hydro, the root of the anion, ic, and then acid. Right, so our hydrogen is basically taking the place of that cation in an ionic compound. Now, it's also important to recognize that HCl would be covalently bonded, right? Hydrogen is a nonmetal, chlorine is a nonmetal. They just very readily will separate in a aqueous or in water solution. Okay, so HCl, that would be hydro. Anion root, chlorine, is chlor. Ic, acid, right? These are nice because they just tell you what it is. Here we have hydrosulfuric acid. So this would be S. Remember, sulfur is a 2- anion. So when you're looking at the name of an acid, you need to ask yourself, how many hydrogens do I need to balance it? In the same way that you balance your ionic compound. So I need 2 hydrogens, so that would be H2S. If the acid has oxygen, that means that it's going to be an acid that's a polyatomic. So with oxygen, immediately look at your polyatomic list. And if you flip your periodic table over and evaluate that polyatomic list, you'll see that by and large, the polyatomic ions either end in ITE or ATE. So in naming our acid, we're going to change our ending from ITE to OUS or ATE to IC. So you have the name of that anion, change the ending, and add acid. So we just want to look at ClO4. So find that, and we can see that that is perchlorate. Yeah, perchlorate. So we're going from ATE to IC. I remember this because if you eat something acidic, it's icky. I don't know. That's just always worked for me. Throw it away if it doesn't work for you. So this would be, right, you name the anion, perchlor, CHLOR, and this is perchlorate, so we go to perchloric and add acid. Now we have ClO2, which I just looked at, and that is chlorite, So that would be chlor, ITE goes to OUS, chlorous acid. Then we have carbonic. So we want to look, if it's ic, we know that it was 8, so we're looking at carbonate, which would be CO3. If you look on your periodic table, CO3 carbonate is a 2-, so I need 2 hydrogens to balance it out. So that would be my formula. Lots of practice in those worksheets. All right, so we have a similar flow chart for acid naming. So does it contain an oxygen, the ion? Anion? If the answer is no, then you do this hydroanionic acid. If it's yes, then you need to look at your endings and change the endings of the root. Okay, the next one would be naming bases. If you named acids, we need to name bases. The only bases that you will be asked to name are going to be hydroxide. So I showed you that neutralization reaction with a proton plus a hydroxide forming water. That's basically the depth of naming bases that you will be expected to get to. So here we have K, so we name the cation. Right, notice OH is negative. You can find that on your polyatomic list and find the charge. Potassium is positive. This would be aluminum hydroxide. Barium hydroxide. Oh, we just did this one. BaOH2. So naming bases is super easy. Okay, the last naming system that we need to know is naming hydrates. So there are certain compounds that we will purchase that can either be like this compound, which I won't name right now because we'll name it together. It can either be a powder or it can actually have water that is in its crystal lattice. So if you remember when we were talking about solids, liquids, and gases, we talked really briefly about that crystal lattice structure. So within the packing of those ions, there's also water. So there's reasons for preferring hydrates. Sometimes it's more stable. It can change melting temperatures and things like that. So this is our method of indicating that it is a hydrate. We use this like kind of fat period, I guess. And then we use a coefficient to indicate the number of water molecules that we have. So CuSO4 should be able to recognize that that is an ionic compound, right? Because Cu is a metal. SO4, we know, right? I have 3 capital letters, so I know that this has to be a polyatomic. I look for Cu and I see it's copper. Then I'm going to go ahead and look at SO4. And SO4 is sulfate. So I only needed 1 copper, so I know that it's copper 2 sulfate. Right? Copper is a transition metal, so I want to go ahead and make sure that I use my Roman numeral to indicate which form of copper I'm working with. Then I have that fat period, and here I'm going to use my prefixes again, so that would be pentahydrate. So here we have Zn, which is zinc. And I have to remember, I don't remember if zinc forms 2 anions. Just to be safe, let's throw in the, I think it only ever forms 2, so I think that's redundant. I don't think, if a transition metal only forms 1 kind of anion, for example, aluminum is always a +3. you don't have to, I have to write it because it's kind of redundant, right? But if you did write it, I wouldn't hold it against you. So that's zinc sulfate, and that would be septahydrate. Hepta. Sorry. Okay. So really the only additional is just having that prefix hydrates. So just putting some pieces together that we've already worked on. All right, so that's all the naming. The rest of this lecture is just going to be a really kind of brief considerations to keep in mind. So one of those things is that we did not, in your textbook, does not talk at all about hydrogen bonding in this chapter, which I think is a little bit of a missed opportunity, but we will talk about hydrogen bonding more in future chapters. But suffice it to say, like, this is a water molecule, and what you'll learn in the lab, or what you'll really be exploring, is that one of the unique qualities of a water molecule is that, so we have our oxygen as our red atom here, and it's bonded to two hydrogens, right, forming H2O. And if you look at your periodic table, you think about that location of our hydrogen and our oxygen, they are relatively close to each other, but we really like to think of our electronegative atoms as being a lot of fun, right? It's a terrible chemist joke. But these are the, like, electron hogs of the chemical world. So fluorine, oxygen, and nitrogen are going to want electrons, and they are going to be the species, if they are bonded to hydrogen and there's another fluorine, oxygen, or nitrogen in the solution, they're going to be able to form hydrogen bonding, which is represented here with these green lines. So covalent bonding, we have a sharing of electrons. Ionic bonding, we have electrostatic force. Hydrogen bonding, you have these more fleeting interactions with each other, right? So like if a covalent bond was being married and a ionic bond was being in a domestic partnership, hydrogen bonding would just be like seeing if you get along, right? You're on like a Tinder date. So here we have our oxygen, we have our hydrogens. Oxygen, again, is an electron hog. So what we see is that water is actually a polar molecule, where the oxygen is going to hog those electrons that are being shared between the hydrogen and the oxygen in our bonds here. So yes, they're sharing an electron, but those electrons are going to be closer or associate more with that oxygen than they do with the hydrogen. As a result, our oxygen is going to be slightly negative in charge, and our hydrogens are going to be slightly positive. Now, if you look at this kind of relationship, here we have our slightly positive hydrogen that is interacting with these kind of transient relationships with our oxygen, right, which is slightly negative. Again, our hydrogen interacting with with an oxygen, which is slightly negative, right? So we have these kind of fleeting attractions between our polar molecules. So oxygen, moving ahead of myself, this is slightly positive, slightly negative. So this is called a polar molecule, because you have one pole that is positive and one pole that is negative. So in these polar molecules, they're going to have this attraction with each other, again, FON. And because of that, there's going to be some very interesting chemistry that takes place. For instance, the fact that ice is more dense as a liquid than it is as a solid, right? That's a fun fact that without we would not exist on this planet. and that is largely due to hydrogen bonding. Okay, so this table, there's a couple things that I just want to draw your attention to. Really, just two things. So the first one is that it is always acceptable to just call water, just to call H2O water. So its systematic name is dihydrogen monoxide, but we just don't really use that very often. We just call it water. So also ammonia is very, very common in chemical reactions. We're going to see it a lot in acid-base chemistry. So this is a compound that is not listed on your polyatomic ion list, and I would just encourage you, if you look on your polyatomic ion list, you'll see that ammonium is NH4. Ammonium is the ammonia cation, so it's gained another hydrogen, or gained a proton, right? So just somewhere on your periodic table, make sure that you know that NH3 is ammonia. So I know this is a lot, it's a lot of naming, you just got to get practice with it, but I do want to just highlight the fact that this is actually important just beyond studying chemistry. So there is a lot of value just to developing scientific literacy. So these are two memes that a couple people on the Facebook have posted in the last few years, and they really show a lack of scientific literacy. So this first example, right, look at Obama, looking so mischievous. So here we have a meme that says, President Obama banned the use of dihydrogen monoxide to torture detainees, yet still allows it to be given to our children at school. Right, so this person was pretty outraged about this. And dihydrogen monoxide is a chemical that's very powerful, right? People die in it. People die without it. It's an acid and it's a base. It's got a lot of crazy properties, all of which make it the powerful chemical that it is, otherwise known as water. Right, so there was a really interesting study, really sad study that was done, where it's a website called, I think it's what is it? It's dhmo.org. And it's just a whole bunch of fake news about science stuff, mostly about dihydrogen monoxide. It's interesting to look at, but it was created in order to judge the scientific literacy of teachers and students in high schools and middle schools, and it was pretty alarming how many people didn't put together that dihydrogen monoxide was water. Another one, this is a fun one that one of my mentors growing up put up. What's in plant-based meats? Right? Titanium dioxide. What whitener used in paint? Propylene glycol. Oh my gosh. Liquid in e-cigarettes. E-cigarettes are dangerous. Methyl cellulose. Whoa. Ferric phosphate. Magnesium carbonate. Oh, and there's this picture of a coal plant or something industrial that looks scary, and it's fake meat doesn't grow on a vine, it's ultra processed. Okay, so fake meat is ultra processed, but everything is made of chemicals, and chemical names are not scary. So unless you let them be scary with your ignorance. So most of these chemicals are also in ice cream, right? So learning how to name chemical compounds not only is good for this class, but it will also allow you to read things like this in your everyday life and be the person who says, this is not something to be afraid of. Derisive means are scary. Titanium dioxide is not. Okay, that's my little PSA. Yep, do it. That's chapter 2. Awesome.